Hello everybody and welcome to Simple Harmonic Motion lesson 3. Now in the last lesson we derived the general equation for simple harmonic motion, which said that A is equal to minus omega squared x, where omega, just like we did in circular motion, we're going to take normally and mainly in this topic as 2 pi over t. Now obviously in the first two lessons of this topic we've been very much looking at simple harmonic motion in general terms. What we're going to move on to today is to now take the simple pendulum, the system that we've used for quite a lot of our examples over the first couple of lessons, and we're going to look at that in more detail and see that if we can derive an equation which can describe the motion of the simple pendulum. So when we look at the simple pendulum, the first thing we need to do is get quite a few definitions down so that we know the symbols that we're using when we're describing the pendulum itself. So I'm going to use the still image, but I'll draw us a diagram over here which hopefully should describe it at the same time as well. The first thing that we need to have down as a definition is the length of the pendulum. So from the pivot point of the pendulum down to the centre of mass of the bob, and we're going to define that as the length of the pendulum. So the length of our pendulum will be L. We also need to look at the angle that the pendulum is at compared to the vertical, which we're going to label as theta. So there is our angle theta there. Now when the pendulum moves, it will follow the arc of a circle. Okay, so if I draw that on there, that green line is the arc that it will follow. So the distance, or at least the arc length, we can label S. Now of course we know that it follows the arc of a circle because the length of the string will remain a constant. To use the physics cliche in a lot of ways, we'll call it a light inextensible string, so therefore it stays at exactly the same length. At this point, unfortunately, we do need to get a little bit technical, and we need to look at different ways that we can define the displacement from the equilibrium position. Now, if you don't necessarily follow what I'm going to be talking about over the next couple of minutes, that's not necessarily a bad thing. It won't disadvantage you in any way. Hopefully you guys who are better at maths and doing further maths as an A level will be able to follow this a little bit closer. But like I said, it's not going to necessarily disadvantage you if you don't understand where I'm going over the next couple of minutes. So, as I said, we're trying to look for some way of measuring displacement from the equilibrium position. And there are three different ways that we can do it. Firstly, we can take, very simply, the arc length. The second way that we can do it is to take the horizontal distance, okay, which I'm going to label there X, and that is horizontal because that's going to make a right angle to the red dotted line, which is vertical, so that's X. The third way that we can look at it is to take the distance in a straight line from the equilibrium position, which I'm going to label Y. So the equilibrium position would have been there. Now if we look at these three terms then, S, X and Y, in terms of theta. Firstly, let's take the arc length. Well, remember from circular motion that theta is defined as the arc length divided by the radius, which is S over L. Next, let's take X. Well, we've got a right angled triangle here with the red dotted line as the vertical. That is the adjacent side. X as the blue line is the opposite side, and the length of the pendulum is the hypotenuse. So therefore, when we look at it, if we take X and L, we can see that sine theta is equal to x over L. Now, y becomes the interesting one because what we have here with the length of the pendulum, y, and the red dotted line is we actually have an isosceles triangle where both the long sides are the length of the pendulum and the shorter side is y. But what we should now be able to see is that as theta gets smaller, sorry, I'm using blue, as theta gets smaller, the angle here between L and y will tend to a right angle. And I'll explain that a little bit more in a moment. But when we take L on the left that we've drawn and y as our two angles, with the red dotted line as the hypotenuse, we can see that tan of theta, which of course is opposite over adjacent, is y over L. Now here comes the sort of mathematical fiddle, mathematical trick that we're going to use. If you may have heard of it, but we're going to use what's called the small angle approximation. Now, the small angle approximation comes from the Taylor expansion of sine theta and tan theta. If you have heard of the Taylor expansion, you can maybe go away and remind yourself what that means. If you don't know what the Taylor expansion is, again, I wouldn't worry about it too much for now. If you are interested, you can go and have a little bit of research on that. Now, what the small angle approximation says is that for small angles, for small theta, that theta and sine theta and tan theta all become approximately equal to each other. Now, what do we mean by a small angle? Really, we're looking for an angle less than 0.2 radians. Now, 0.2 radians is approximately 11 degrees. So really, as a rule of thumb, we're trying to keep theta less than 10 degrees in order for that approximation to hold true. Now, what that means for our derivation, of course, is that, yes, okay, we've got three different ways of looking at the angle and the horizontal displacement, the displacement x from the equilibrium position. But what the small angle approximation is telling us is that really underneath 10 degrees, less than 10 degrees, all three of those become approximately equal to each other anyway. Now, if you were to do this at a university level, then you would be using this equation here, theta is equal to s over L, in order to carry on with the derivation. But what we're going to do, based on the fact that we are applying this small angle approximation, is we're actually going to take this one here, sine theta is equal to x over L, and it will, as you can see, become approximate to the proper, in inverted commas, way of doing this derivation. So, as I said, I'm sorry if I did sort of throw you a little bit with what I've said on the last slide. We all sort of need to come back now. Everything from here on in should be accessible to everybody. So the next stage of the derivation is we need to look at the forces that are acting on the pendulum. Unfortunately, there are only two forces. Firstly, in the string acting back up, we have the tension in the string. And secondly, we have the weight of the bob, which will act straight down. Now, if I'll just redraw that over here, here is the bob. The tension in the string will be acting in a direction up there. I know I've exaggerated the angle, but that's just to hopefully make you see what's going on here. And the weight is acting straight down. Now, of course, we've got a little bit of a problem here. We've got two forces that are not acting perpendicular to each other. We therefore need to resolve one of these forces. So we've got two choices. We can either resolve the tension into its vertical and horizontal components, or we can resolve the weight into its components parallel and perpendicular to the string. And in fact, it's the second option that we're going to take. So to look at the components then, we have one component there, and we have one component there. So the first component, this is going to be the parallel component, and this component here will be the perpendicular component. Now obviously, next we're going to need some form of angle on here to be able to resolve this weight properly. If we go back to the diagram, we can see that, and I've changed colours, but doesn't matter, we've got theta here. So we have a vertical line and we have an angle to the string. Now when we come back over to the main diagram that I've drawn on the right hand side, in fact we can do it on the left, it doesn't really matter, because the weight is acting straight down and this black dotted line is acting, or is in the direction straight down, those two lines are parallel to each other. The parallel component, by definition, is parallel to the string, and therefore the dotted line and the tension with the angle of theta is exactly the same as the weight acting straight down and the parallel component, and therefore there is our angle theta. Next then we can resolve. So the parallel component is the adjacent component, and therefore that component will be mg cos theta, and the perpendicular component will be mg sin theta, because that's not the adjacent, that's the opposite component. So now we need to look at these components and try and compare them with the tension. So the main one we need to look at is the parallel component, mg cos theta. And if we go back to what I said earlier about the length of the string, well, the length of the string doesn't change. Now, in order for that to happen, there must be no net force acting parallel to the string. In other words, there is no force which is acting to either stretch or compress the string. What we can therefore say, because there is no net force, so the force parallel must equal 0, and therefore the mg cos theta component must equal the tension. When we come back to the diagram, those two forces, so the mg cos theta and the t, are therefore cancelling each other out. What we're left with then is that the only force which is acting, or the net force I should really say, that is acting on the bob, on the pendulum, is mg sin theta. That therefore is our net force. Now that net force is the force that is causing the pendulum to want to return back to the equilibrium position, and we therefore call it the restoring force. So bringing that onto the next slide then, the restoring force, the net force, is mg sin theta. Now when we go back to the second slide, and we were talking about the different ways of approaching the displacement from the equilibrium position, we said that sin theta was x over L. We can substitute that in, therefore, and say that F is equal to mg multiplied by x over L. Now I will tidy that up in just a moment. The one thing that we need to add in though, I'll put it in first, is the negative sign. Now the reason why we need to put the negative sign in there is just to make sure that we're getting the vectors correct. We know that the restoring force is acting to the right, but the way that we've defined it, where the blue line is x is equal to 0 and we've defined x therefore to the left, we've got two vectors therefore acting in opposite directions. So we must at that point introduce the minus sign to make the direction of the two sides of the equation make sense. So to tidy that equation up, we have minus mgx over L. Okay, the next stage then is to do something with the left hand side. So at the moment we've got force, but at this point we will substitute in on the left hand side with Newton's second law. Now at this point, and I know I've put the simplified version of Newton's second law on the screen, hopefully we can agree that the mass of that pendulum bob won't change. It will therefore be a constant, and therefore rather than doing the rate of change of momentum version, we can very happily simplify it to the F equals ma version. Now that, of course, F equals ma, remember, is a general equation. So whenever a force is acting, we can apply happily that equation. We're just now applying it to this specific simple pendulum example. So when we do that substitution, we get ma is equal to minus mgx over L. The next stage then, we can see that the m's will cancel out. Now normally, especially if we were doing this from a purely maths point of view, we just cross out those m's and move on, but of course as physicists we need to make sure that we understand why we're doing that. Now what that means in our derivation is that the mass is irrelevant. In other words, it doesn't matter what the mass of that pendulum bob is. That bob, the one that I showed you in the video and in the diagrams, is made of metal. We could have had one that was made of polystyrene. As long as the length of the pendulum from the pivot to the centre of mass of the bob remains the same, it has absolutely no bearing on this derivation and the final equation that we're going to get. So we are almost there. Just bear with me for one last slide and we'll get the equation that we're looking for. So let's again just bring that equation over from the last slide. A is equal to minus g times x over L. Now again, this is where we do a little bit of a trick. It's not necessarily a controversial one, but you'll have seen this kind of thing before. Underneath that equation, I'm now going to write the general equation for SHM that we derived in the last video. And just like we do when we're looking at the equation of a straight line, so putting y equals mx plus c underneath and seeing what relates to the gradient and what relates to the y-intercept and all that kind of stuff, we can see that we've actually got two equations which are basically saying the same thing, or at least in the same format. We've got our acceleration, we've got the minus sign, and we've got x, the displacement. What that leaves us with is the g over L, and in the general equation we've got the omega squared. Just like we would do when we're looking at the equation for a straight line, we can therefore equate the two. So we can say that omega squared is equal to g over L. The rest of this is now just algebraic manipulation, so we can square root. We can say that omega is equal to the square root of g over L, but then of course we can remember that we substitute in 2 pi over t for omega, root g over L. We can now take the inverse of both sides of the equation to say to us t over 2 pi is equal to the square root of, sorry, I'm taking the inverse, L over G, and then finally we can multiply both sides by 2 pi to end up with the equation t is equal to 2 pi multiplied by the square root of L over G. And there we have it. That now is the equation for the time period of a simple pendulum. finally then, just to define all of our terms and redefine all of our terms, t is the time period which will be measured in seconds. L is the length of the pendulum, which will be measured in meters, and G is the acceleration due to gravity. Which on Earth at least is 9.81 metres per second squared. So here then is your question for this video. Calculate the time period of a simple pendulum of length 1.05 metres, A on the Earth and B on the Moon. And as you can see there, I've told you that acceleration due to gravity on the Moon is 1/6 of the acceleration due to gravity on the Earth. So as usual, pause the video, go away and work out your answers. Once you've got those answers, come back and I'll go through the answers. So let's do on the Earth first. So obviously T is equal to 2 pi root L over G, which is equal to 2 pi root of 1.05 over 9.81. When we put that into our calculator, we get 2.0556, and therefore the question is given in 3 sig figs, so we will round to 2.06 seconds. Of course, for B, we're just going to take the same approach. So T is equal to 2 pi root L over G. So 2 pi times root of 1.05 over 9.81 divided by 6. That gives us an answer on the calculator of 5.0351. And therefore we can round that again to 3 significant figures and we'll get 5.04 seconds. Now at this point, if that's how you've done it, if you've just obviously kept the same workings in your calculator and just chucked the divided by 6 in there, there's absolutely nothing wrong with that. But let me just show you a little trick that we can use, which is probably more of a long-winded way of doing it for this question, but it's a perfect question to show you how we can do that. Now firstly, if we say that the time period on the Earth is 2 pi root L over G on the Earth, and we also say that the time period on the Moon is equal to 2 pi root L over G on the Moon. From this part of the question, if we translate that into an equation, what it's telling us is that G on the Moon is equal to G on the Earth divided by 6. If we substitute that now into there for G on the Moon, what we end up with is time period on the Moon is equal to 2 pi root L over G on the Earth divided by 6. Now we've got divided by, that's going to end up on the top, so that's 2 pi root of 6L over G on the Earth. Playing around with that square root a little bit, I'm just going to now write that the time period on the Moon is 2 pi root L over G on the Earth multiplied by the square root of 6. Now at this point, what we've got here, 2 pi root L over G on the Earth, is exactly what we've got up here. It is the time period on the Earth. So our equation now says that the time period on the Moon is equal to the time period on the Earth multiplied by the square root of 6. Now, if you still got the answer from part A, brilliant. If not, it won't take you long to plug it back into your calculator. Try it out and do exactly what we've got there. So 2 pi root of 1.05 over 9.81. And in your calculator, you can put multiplied by root 6. And what you'll find is that you'll get exactly that answer that we got for the time period on the moon. Now, as I said, that's probably a little bit of a long-winded way of doing it for this particular question, but it's exactly that kind of thinking that will be useful to you, especially when it comes to the multiple choice questions, or for anybody really that's looking at doing maths or physics or anything like that at a higher level at university, or obviously for engineering or anything like that. That's a really good method to use, and that kind of algebraic method, if you can get around that and get your head around that and get used to that, in the future for the vast majority of questions, it will make life easier for you. So to summarise the lesson then, what we've looked at in this video is the theory of the simple pendulum, and then obviously the key equation that we've got out of that is the simple pendulum equation, which is T is equal to 2 pi root L over G. So that's it for this lesson. As usual, any issues, please get in contact with me. Otherwise, I'll see you in the next video.